Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most unsettling and fascinating questions science has ever dared to ask. What is consciousness really? And more specifically, could it be connected in some deep and unexpected way to the strange rules of the quantum world? Before you settle in and get comfortable, I gently invite you, only if you feel like it, to like this video, subscribe to the channel, or leave a comment telling me where in the world you're listening from and what time it is right now. It's always quietly comforting to know how many different corners of the night we're sharing together. Now you might want to dim the lights, maybe let a fan hum softly in the background, or rest your head somewhere warm. And if your mind begins to drift as we go, that's perfectly fine. You don't need to hold on to every idea. We'll be moving slowly, and nothing here needs to be solved tonight. This isn't a story about instant answers. It's a story about a gap that has quietly followed science for more than a century. A gap between equations and experience, between descriptions of the brain and the simple fact that you are here, feeling something right now. So let's begin, gently, by noticing that strange fact together. There is something quietly remarkable happening right now. You are listening. You are aware. There is a sense of being present, of occupying this moment, that doesn't need effort or explanation. It's simply there. From the outside, science has become very good at describing what a human being is made of. We know the elements in your body were forged in ancient stars. We know how atoms bind into molecules, how molecules form cells, and how billions of cells assemble into tissues and organs. We know how electrical signals travel along neurons, how chemical messengers cross tiny gaps, and how vast networks of brain activity coordinate movement, language, and memory. And yet none of those descriptions quite explain the most obvious thing of all, that this feels like something. Not metaphorically, not poetically, but literally. There is a point of view here, a private inner movie, a soft, continuous sense of being you that no microscope has ever captured and no scan has ever directly displayed. From the outside, your brain looks busy. From the inside, it feels like experience. This difference is easy to overlook because it's so familiar. You've never known a moment without awareness, even when it fades or flickers. But if you pause for just a second, it becomes deeply strange. Why should matter, arranged in a particular way, generate a first-person perspective at all? A rock doesn't wonder what it's like to be a rock. A thermostat doesn't feel warm or cold. A computer processes information, but as far as we can tell, it doesn't feel the weight of its own calculations. And yet here you are, a physical system in a physical universe, accompanied by sensations, thoughts, emotions, and memories. The universe somehow is experiencing itself through you. Science has learned how to predict behavior with astonishing accuracy. It can tell us which brain regions light up when you see a color, remember a face, or feel pain. It can describe correlations between neural activity and reported experience. These are called neural correlates, patterns that reliably appear when certain experiences are present. But correlation is not explanation. Knowing that a region of the brain becomes active when you feel sadness doesn't explain why sadness feels heavy, or why joy feels light, or why the color red feels different from the color blue instead of simply being another data label. You could, in principle, map every signal in the brain and still be left asking the same quiet question. Why does any of this feel like anything at all? This is not a minor technical puzzle. It's not a missing piece that more computing power alone seems likely to fix. It's a conceptual gap, one that sits at the foundation of how we understand reality. Some scientists believe this gap will eventually close as neuroscience becomes more detailed. Others suspect something deeper is missing from the story, that consciousness may not fit neatly into the classical picture of the universe as a machine made of predictable parts. And this is where things begin to get interesting, because physics has been here before. At the beginning of the 20th century, physicists thought they had the universe largely figured out. Space, time, matter, and energy followed clear rules. The universe was understandable, predictable, and solid. Then, very quietly, experiments began to reveal cracks in that certainty. Particles behaved like waves. Measurements changed outcomes. Certainty dissolved into probabilities. Reality, at its smallest scales, refused to behave like the world we experience directly. The quantum world didn't just add new details to physics. It forced scientists to rethink what it even means for something to exist. And now, more than 100 years later, some researchers are asking a question that makes many physicists deeply uncomfortable. What if the gap in our understanding of consciousness is connected to the same strange place where physics once lost its footing? What if awareness is not merely a byproduct of neural activity, but is tied, in some subtle way, to the mechanisms that turn possibilities into reality? This idea doesn't claim that consciousness creates the universe. It doesn't suggest mystical powers or hidden forces. Instead, it asks something quieter and more unsettling. Whether the rules we use to describe matter and energy might be incomplete without accounting for experience itself. Tonight, we're not trying to prove that consciousness is quantum. We're not trying to declare a final answer to one of the hardest questions science has ever faced. We're simply following a trail of ideas, carefully, skeptically, and gently, to see where it leads. For now, it's enough to notice the strange fact that started it all. That the universe contains not just stars and particles, but moments like this one. A moment where something is happening and someone is here to notice it. And as we rest with that thought, the story begins to drift toward the place where certainty softens and possibility quietly takes over. If we step back from that quiet sense of being present and look at the human mind from the outside, what we see is astonishingly complex but also surprisingly mechanical. The brain is an object you can weigh, scan, and map. It sits inside the skull, consumes energy, and follows physical laws just like every other organ. Over the last century, neuroscience has learned how to observe it in remarkable detail. We can watch neurons fire in real time. We can track electrical rhythms spreading across networks. We can even predict with growing accuracy what someone is likely seeing, hearing, or thinking about based on patterns of activity. From this perspective, the brain looks like a sophisticated biological machine. Signals arrive, signals are processed, signals are sent onward. Information flows through circuits shaped by past experience and current input, and this success is real. Neuroscience has not failed. In many ways, it has succeeded beyond anything earlier generations could have imagined. But success can sometimes hide a deeper question. When researchers place someone in a brain scanner and ask them to look at a red object, certain areas of the visual cortex become active. When the person hears music, other regions light up. When they remember a childhood home, still other patterns appear. Over time, scientists build maps linking experiences to neural activity. These links are called neural correlates of consciousness. It's a careful term chosen on purpose. A correlate is something that reliably accompanies something else. It does not claim to be the cause or the explanation. It simply says, when this experience happens, this activity is present, and here is where the gap quietly opens. Imagine you're given a complete, perfect map of a city. Every street, every building, every electrical line is drawn in exquisite detail. You know where traffic flows, where lights turn on at night, where people tend to gather. but the map itself never tells you what it feels like to stand in that city at sunset. It does not convey the warmth of the air, the sound of distant voices, or the sense of familiarity or longing that might arise in a particular place. In a similar way, brain maps describe structure and activity, but they do not capture experience itself. You can point to a cluster of neurons and say, "This pattern appears when pain is reported." But nothing in the pattern explains why pain hurts, rather than appearing as a neutral signal or a silent alert. You can trace circuits involved in colour vision, but the diagrams do not contain redness, blueness, or brightness. They contain only relationships and signals. This is not a complaint about neuroscience, it is a recognition of its scope. Neuroscience explains how the brain processes information, coordinates action, and integrates sensory input. It explains how damage to certain areas can alter perception or behaviour. It explains why anesthesia disrupts awareness, and why sleep changes the texture of experience. But even with all of this, a subtle question remains untouched. Why should any of this processing be accompanied by a point of view? From a purely functional standpoint, it seems possible to imagine a system that behaves exactly like a human being, responds appropriately to every stimulus, reports internal states, and yet experiences nothing at all. Philosophers sometimes call this a philosophical zombie, not as a serious claim about reality, but as a way of highlighting the explanatory gap. If such a system is conceivable, then behaviour alone does not guarantee experience, and if behaviour does not guarantee experience, then mapping behaviour-related brain activity does not fully explain why experience exists. This is why some scientists say that consciousness is not just another problem, but a different kind of problem. In most areas of science, explanation works by breaking things into parts and showing how those parts interact. We explain storms by understanding air pressure, temperature, and moisture. We explain life by understanding chemistry, genetics, and evolution. Each layer builds on the one below it, but consciousness resists this layering. No matter how detailed the explanation becomes, it always seems to stop just short of the thing that matters most, the feeling itself. The presence of experience does not appear in the equations, the diagrams, or the simulations. It appears only from the inside. This has led to two broad responses within science. One response says, in effect, be patient. According to this view, consciousness will eventually be explained entirely in terms of brain processes once we understand them well enough. The feeling of mystery comes from incomplete knowledge, not from a fundamental gap. The other response is more cautious. It suggests that something about our current framework may be missing an ingredient, not something mystical, but something conceptual. Perhaps consciousness is not an emergent detail that appears only at the end of a long chain of complexity. Perhaps it is woven more deeply into the structure of reality than we have assumed. This second response does not deny the brain. It does not reject neuroscience. Instead, it asks whether the brain might be a participant in a larger process, rather than the sole source of experience. And this is where the conversation begins to drift, almost inevitably, toward physics. Because physics too once believed it had the universe neatly organised, and physics too discovered that at a certain scale, its familiar concepts no longer worked as expected. In the quantum world, particles do not have definite properties until interactions occur. Outcomes are not fully determined in advance. Possibility plays a role that classical physics never anticipated. Some researchers wonder whether the gap we encounter in consciousness mirrors the gap physics encountered a century ago. A place where intuition fails, where description outpaces understanding, and where something fundamental refuses to be reduced to simpler parts. This does not mean that the brain is doing quantum physics in any obvious or dramatic way. It means only that the tools we use to describe matter and energy may not be sufficient to describe experience. For now, we're left with a strange balance. We can see the brain working, we can measure its activity, we can influence it with chemicals, electricity, and injury. And yet, the simple fact that there is something it is like to be you remains quietly unexplained. As this realization settles in, the question gently shifts. Not where in the brain is consciousness, but what kind of thing would consciousness have to be in order to exist at all? And that question leads us slowly and carefully toward a realm where certainty fades and the universe reveals a more subtle way of being. By now, a quiet tension has begun to settle into the story. On one side, there is the brain, active, measurable, and astonishingly intricate. On the other side, there is experience, immediate, private, and impossible to observe from the outside. The two are clearly connected, and yet the connection itself remains strangely opaque. This tension is what philosophers and scientists refer to as the hard problem of consciousness. The name sounds intimidating, but the idea behind it is simple, almost disarmingly so. Why does physical processing feel like anything at all? Not how the brain processes information, not how it reacts to stimuli, not how it produces behavior or speech. Those questions, difficult as they are, belong to what are sometimes called the easy problems. Easy not because they are trivial, but because they follow a familiar scientific pattern. You can imagine, at least in principle, how more data, better models, and improved experiments might eventually explain them. The hard problem is different. It asks why any of those processes are accompanied by an inner point of view. Why there is something it is like to see a colour, hear a melody, or feel a quiet sense of calm as you drift towards sleep. To understand why this is such a stubborn puzzle, it helps to notice how explanation usually works in science. When we explain temperature, we talk about the average motion of molecules. When we explain sound, we talk about vibrations travelling through a medium. In each case, something that feels immediate and qualitative is explained in terms of underlying structure and dynamics. But with consciousness, that move seems to fall short. You can describe the motion of neurons, the exchange of chemical signals, and the flow of electrical activity in exquisite detail. You can even build machines that mimic many of the brain's functions. Yet none of that description seems to contain experience itself. The feeling does not appear to be hidden inside the parts, waiting to be discovered. It appears to exist at a different level altogether. This is why the hard problem is sometimes described as a gap between third-person descriptions and first-person reality. Third-person descriptions are what science does best. They're objective, shareable, and measurable. Remember the brain scanner, the graph, the data point. First-person reality, by contrast, is immediate and private. No one else can directly access your experience. They can only infer it from what you say or do. And here is the uncomfortable part. Even if you knew everything there was to know about the physical state of a brain, it is not obvious that this knowledge alone would tell you what it feels like to be that brain. This realization has led some thinkers to suggest that consciousness might not be something that emerges only when systems become sufficiently complex. Instead, it might be something more fundamental, not in the sense of being mystical or supernatural, but in the sense of being woven into the basic fabric of reality. This idea can feel unsettling, because it challenges a deeply ingrained assumption. We're used to thinking of consciousness as a late arrival in the universe. First came particles, then atoms, then stars, then planets, then life, then brains, and finally awareness. Consciousness, in this view, is a delicate flower growing at the very top of a long evolutionary tree. But the hard problem invites a different question. What if consciousness is not the flower at the end, but part of the soil itself? This does not mean that rocks are thinking or that electrons have thoughts. It means only that the ingredients required for experience may not suddenly appear at the level of neurons. They may exist in some primitive or potential form much deeper down. If that sounds strange, it is worth remembering that physics has already taught us to be cautious with intuition. There was a time when matter seemed solid and indivisible. Then atoms turned out to be mostly empty space. There was a time when time itself seemed absolute. Then it turned out to stretch and bend. There was a time when particles were thought to have definite properties at all times. Then quantum mechanics revealed a world where certainty gives way to probability until interaction occurs. In each case, reality turned out to be subtler than our everyday experience suggested. So when researchers ask whether consciousness might be connected to the same quantum domain where certainty softens into possibility, they are not abandoning science. They are following a familiar pattern, noticing where current explanations stop working, and asking whether a deeper framework might be needed. At this stage, it's important to slow down and clear away a common misunderstanding. The hard problem does not claim that consciousness causes physical events in some magical way. It does not say that thoughts rearrange atoms or that awareness floats free from the brain. Instead, it highlights something more modest but more profound, that our current physical descriptions, as successful as they are, do not explain why there is an inner life at all. You can think of it like this. Imagine reading a detailed recipe. It tells you the ingredients, the temperatures, the timing, and the steps. You can follow it perfectly. But no matter how carefully you read, the taste of the final dish is not contained in the words. The taste only exists when the dish is actually made and experienced. The recipe is not wrong. It is simply not the same kind of thing as the experience. In a similar way, the brain's processes may be like a recipe for experience without being the experience itself. The hard problem asks why following the recipe produces taste at all. For some scientists, this question is simply too vague to be useful. They prefer to focus on what can be measured and manipulated. For others, the question is unavoidable. Ignoring it feels like ignoring the most obvious feature of the universe we inhabit. And so the conversation splits, not into believers and skeptics, but into different intuitions about what counts as an explanation. Is consciousness something that will eventually be explained entirely in terms of neural mechanisms once we understand them well enough? Or is it a sign that our picture of reality is missing a piece, something that does not fit neatly into classical categories of matter and energy? This is where the story gently leans toward quantum physics. Not because quantum theory is mysterious, but because it already forced science to revise its understanding of what is real, what is possible, and what it means for something to exist. As these questions settle in, we find ourselves standing at the edge of two great mysteries. One is the mystery of matter at its smallest scales. The other is the mystery of experience at its most intimate. And somewhere between them, a quiet idea begins to take shape, that the gap we feel when trying to explain consciousness may be pointing, not to failure, but to the next place where understanding has yet to unfold. As the question of consciousness lingers in the background, the story now drifts toward another moment in scientific history when confidence quietly dissolved. At the end of the 19th century, physics appeared complete. The universe, it seemed, was made of solid objects moving through space and time according to precise rules. If you knew the position and motion of every particle, you could, in principle, predict the future forever. Reality was a clockwork mechanism, elegant and reassuring. And then, very gently at first, that picture began to crack. Experiments probing the smallest scales of matter revealed behavior that made no intuitive sense. Light, once thought to be a smooth wave, sometimes behaved like a stream of tiny packets. Particles, once thought to be solid points, spread out like ripples on water. Attempts to pin them down led not to certainty, but to strange clouds of possibility. This was the birth of quantum physics. One of the most unsettling discoveries was that particles do not always have definite properties before they are measured. Instead of occupying a single state, they exist in what physicists call superposition. That word sounds technical, but the idea can be softened. Imagine a musical chord instead of a single note. The chord contains several notes at once, not because it is confused, but because its nature allows multiple tones to coexist. Only when you focus on one note, perhaps by isolating it with your ear, does it separate from the whole. In a similar way, a quantum particle can exist in multiple possible states at once, not as a trick of ignorance, but as a genuine feature of reality. Until something happens to narrow those possibilities, the particle is not committed to a single outcome. This was not merely strange, it was profoundly unsettling. Because it suggested that reality, at its foundations, is not made of definite things, but of potential ones. The universe, it seemed, carries possibilities forward until interactions force a choice. This led to another difficult idea, often described with the word collapse. Again, the word can feel harsh, so it helps to think of it gently. Collapse is the moment when many possibilities give way to one actual outcome. It is not an explosion or a failure, it is a transition from openness to specificity. Before collapse, a particle's future is spread out like mist over a field. After collapse, something definite has happened. A spot appears on a screen, a detector clicks. A result is recorded. The unsettling question is not that collapse happens, but why and when it happens. In classical physics, measurement simply reveals a property that was already there. In quantum physics, measurement seems to play a more active role. The act of interaction does not merely uncover reality. It helps bring one version of reality into being. This raised a troubling puzzle. What exactly counts as a measurement? Is it a machine? Is it the environment? Is it any interaction at all? Early interpretations even flirted with the idea that consciousness itself might be involved. Not because awareness has magical powers, but because measurement was so difficult to define without reference to observation. Most physicists today are cautious about that idea. They prefer explanations that do not rely on minds, and yet, the puzzle remains unresolved. There is still no universal agreement on what precisely causes collapse, or whether collapse is even the right way to think about what happens. Some interpretations suggest that all possibilities continue to exist, branching into multiple realities. Others propose that collapse is an objective physical process, triggered when systems reach certain limits. Still others suggest that interaction with the environment gradually suppresses quantum possibilities, making the world appear classical. What matters for our story is not which interpretation is correct, but what they all have in common. They all challenge the idea that reality is fully defined at all times. At the deepest level we know how to probe, the universe does not present itself as a collection of fixed facts. It presents itself as a landscape of probabilities that become definite only through interaction. This is where the parallel with consciousness begins to feel less accidental. Conscious experience, too, has a curious relationship with possibility and actuality. Before you make a decision, multiple options feel open. Before a memory settles, it can feel fluid. Before attention locks onto a sensation, the background remains diffuse and undefined. This does not mean that the mind is performing quantum calculations in any simple way. It means that both physics and experience confront us with the same philosophical tension, the transition from many possibilities to one reality. And just as physics had to expand its conceptual framework to accommodate quantum behavior, some researchers wonder whether our understanding of consciousness may require a similar expansion. It is important here to move carefully. Quantum physics is not mysterious because it is vague. It is mysterious because it is precise in ways that defy intuition. Its predictions are extraordinarily accurate. Its mathematics works. What fails is not the theory, but our everyday expectations about how the world should behave. In the same way, the difficulty with consciousness may not be that it is unknowable, but that our current conceptual tools are mismatched to the task. We're trying to explain first-person experience using frameworks designed to describe third-person objects. Quantum physics taught science an important lesson. That reality does not have to conform to the categories we find comfortable. It can be probabilistic without being chaotic. It can be subtle without being supernatural. As we sit with this idea, the question quietly evolves. If the universe already contains a mechanism for turning possibility into actuality, could that mechanism be relevant to the emergence of experience? Could consciousness be connected not to particles as tiny objects, but to the process by which reality itself becomes definite? This is not a claim. It is an invitation to consider whether the gap we encounter when explaining consciousness is pointing us toward the same strange territory where physics once learned to let go of certainty. And with that thought, the story continues to drift deeper toward the question of what measurement really means and whether the observer is as irrelevant as we sometimes hope. As the quantum picture settles in, a quieter question begins to take shape beneath it. If reality at its smallest scales is made of possibilities rather than certainties, then what exactly turns those possibilities into the single, definite world we experience? This question sits at the heart of quantum physics, and it is one physicists have wrestled with for more than a century. Not because the mathematics fails, but because the meaning behind the mathematics remains elusive. In everyday life, measurement feels straightforward. You check the temperature, and the thermometer gives a number. You step on a scale, and it shows your weight. In these cases, measurement is passive. It simply reveals something that was already there. But in the quantum world, measurement appears to play a more active role. Before a quantum system is measured, it is described not as being in one specific state, but as existing in a range of possible states. This range is not guesswork. It is a precise description of how likely different outcomes are to occur. Physicists represent this using mathematical objects that encode probabilities, but we don't need those symbols here. What matters is the idea itself. Think of a weather forecast rather than a snapshot. Before tomorrow arrives, the forecast contains several possibilities. Rain is likely, sunshine is possible, clouds are almost certain. None of these outcomes has happened yet, but all of them are part of the description of the future. When tomorrow arrives, only one version becomes real. The rain either falls or it doesn't. The range of possibilities narrows into a single outcome. Quantum systems behave in a surprisingly similar way. Before measurement, they are described by a spread of potential outcomes. After measurement, one result appears and the others vanish from relevance. This narrowing is what physicists call collapse. Not a dramatic collapse, but a quiet selection, a settling, a moment when uncertainty resolves into fact. The unsettling part is that physics does not offer a single, agreed-upon explanation for why this happens when it does. Some interpretations suggest that collapse is not a fundamental process at all, but an illusion created by interaction with the environment. As quantum systems interact with countless surrounding particles, their delicate possibilities become scrambled and effectively hidden. This process is known as decoherence, and it helps explain why the world looks classical and stable at larger scales. Other interpretations propose that collapse is real and objective, triggered when systems reach certain thresholds. In these views, nature itself enforces limits on how much possibility can persist. Still others suggest that all possibilities continue to exist, branching into separate, non-communicating realities. In that picture, there is no collapse, only divergence. Each outcome happens, just not all in the same world. What unites these interpretations is not agreement, but discomfort. They all struggle with the same underlying question. At what point does potential become actual? And what, if anything, marks that transition? Early in the history of quantum mechanics, some physicists wondered whether observation itself might play a role. After all, measurement often involved a conscious observer reading an instrument. It was tempting to think that awareness might be the final step that turns possibility into reality. Most physicists today resist that idea, not because it is absurd, but because it introduces something difficult to define into a theory that otherwise works with remarkable precision. Consciousness, after all, is not something physics knows how to quantify, and yet the observer question never fully disappears. If measurement is not just reading a pre-existing value, but participating in the outcome, then understanding measurement becomes inseparable from understanding interaction. And interaction, in the end, always involves systems that register change. A detector registers a particle, a screen registers a mark, a brain registers a sensation. Each of these is a physical system transitioning from one state to another. This is where the parallel with consciousness becomes harder to ignore. Conscious experience itself seems to involve a similar transition. Attention selects one sensation from a field of many. Perception crystallizes into a specific experience. Thoughts arise from a background of potential associations and then fade again. This does not mean that consciousness causes quantum collapse. That claim goes far beyond the evidence. Instead, it suggests something subtler, that both physics and experience involve processes where possibilities narrow into actualities. In physics, this narrowing is formalized with equations and probabilities. In experience, it is lived directly as the flow of awareness. Some researchers have wondered whether these two processes might be related, not because the mind controls particles, but because both may rely on a deeper principle that governs how information becomes definite. Here, the idea of information quietly enters the story. In modern physics, information is not just a human idea, it is a measurable quantity. It can be stored, transferred, and transformed. Some physicists even argue that information is more fundamental than matter itself, that particles are simply ways information organizes in space and time. If this is true, then the act of measurement is not just about detecting particles, it is about updating information. A system moves from a state of uncertainty to a state of definiteness, from a spread of possibilities to a specific record. Consciousness, too, seems intimately tied to information. Experiences are differentiated, they have structure, they are not random noise. There is an internal coherence to awareness, a sense of continuity and organization. This has led to a provocative but careful question. Could consciousness be related in some way to the process by which information becomes definite? Again, this is not a claim of identity. It is a suggestion of alignment, a hint that the boundary between possibility and actuality might be a place where physics and experience quietly meet. At this stage, it is important to remain grounded. Quantum theory does not require consciousness to function. Experiments work whether or not anyone is watching. The universe does not wait for human awareness to proceed, and yet, the fact remains that our deepest physical theory still struggles to explain how and when reality settles into the form we observe. At the same time, our understanding of consciousness struggles to explain how physical processes give rise to experience. Two mysteries, different domains, a similar shape. As these ideas hover gently together, the story prepares to move toward a proposal that attempts to connect them without abandoning scientific rigor. A proposal that does not place consciousness outside physics, but within its unfinished edges. For now, it is enough to notice the shared pattern. That both the quantum world and conscious experience involve transitions from many to one, from openness to specificity, from potential to presence. And with that quiet symmetry in mind, the path ahead begins to narrow, not toward certainty, but toward a more precise question about where, in the physical world, such transitions might actually occur. As the idea of measurement settles, another question quietly steps into view. It is not loud or dramatic, but it has lingered in the background of quantum theory from the very beginning. If measurement is the moment when possibility becomes reality, then what exactly performs that measurement? At first glance, the answer seems simple. A measuring device does, a detector clicks, a screen lights up, a photographic plate records a mark. These are physical systems interacting with other physical systems, and nothing more needs to be said. And yet, when physicists try to describe this process precisely, something unexpected happened. Every measuring device is itself made of particles. Those particles, at the smaller scale, must also obey quantum rules. If so, then the measuring device should also exist in a spread of possibilities, just like the particle it is measuring. This leads to a strange chain. A quantum system is measured by another quantum system, which is measured by another, and so on. At no point does the theory clearly specify where the chain ends and a single outcome becomes real. This is sometimes called the measurement problem, but the name can be misleading. It is not a technical flaw in the equations. The equations work beautifully. The problem is conceptual. The theory describes how probabilities evolve, but it does not clearly describe how one probability becomes the reality we experience. Early physicists noticed this unease almost immediately. Some suggested that the environment itself plays the decisive role. When a quantum system interacts with countless surrounding particles, its delicate possibilities are rapidly scrambled. This process makes superpositions effectively inaccessible, giving rise to the stable, classical world we observe. This explanation, known as decoherence, is powerful and widely accepted. It explains why we do not see cats in two states at once, or chairs smeared across space. It explains why the everyday world feels solid and definite. But even here, something subtle remains. Decoherence explains why interference between possibilities disappears. It explains why outcomes become stable, but it does not, by itself, explain why one specific outcome is experienced rather than another. It explains the loss of visible superposition, not the selection of a single lived reality. In other words, decoherence explains why the world looks classical, but not why this particular version of events is the one we find ourselves in. It is at this delicate point that consciousness historically entered the discussion not as an answer, but as a question. Some early interpretations suggested that awareness might play a role in finalizing outcomes. The idea was not that human minds control reality, but that measurement, in the deeper sense, involves something registering an outcome as definite. This suggestion made many physicists deeply uncomfortable, and for good reason. Consciousness is not something physics knows how to define, measure, or include in equations. Introducing it risks turning a precise theory into a vague one. Over time, most physicists set this idea aside. They focused instead on interpretations that keep consciousness out of the fundamental machinery of physics, and this approach has been enormously successful. Quantum theory works. It predicts experimental results with astonishing accuracy. Still, the question never fully vanished, not because consciousness is mysterious, but because measurement remains conceptually unresolved. Even today, there is no single interpretation of quantum mechanics that commands universal agreement. Different frameworks offer different answers to the same underlying puzzle. Some say collapse is not real. Some say it is real, but rare. Some say it is inevitable, but observer-free. What unites these views is an attempt to explain how definite experience arises from indefinite description. And this is where the parallel with consciousness becomes difficult to ignore. Consciousness, too, is the place where indefiniteness gives way to specificity. Before you focus your attention, your sensory world is diffuse. Before a thought fully forms, it exists as a vague tendency. Before a decision is made, multiple options feel open. Experience itself seems to involve constant acts of selection. Not selection in the sense of choosing freely at will, but selection in the sense of narrowing. One sound comes into focus. One image stands out. One thought becomes clear while others fade into the background. This does not mean that consciousness is a measuring device for the universe. It means that both physics and experience involve transitions from many to one, from open possibility to concrete reality. Some researchers have wondered whether this resemblance is more than poetic, whether the same principles that govern the emergence of definite outcomes in physics might also be relevant to the emergence of conscious moments. At this point, it is important to draw a careful boundary. Nothing in quantum physics requires consciousness to operate. Experiments run perfectly well without human observers. Automated detectors produce results whether or not anyone is watching. The universe does not pause for awareness. The question is not whether consciousness is necessary for physics, but whether physics, as currently formulated, fully accounts for the existence of consciousness. This is a subtle but crucial distinction. Instead of asking whether consciousness collapses wave functions, some researchers ask a gentler question. Could the processes that give rise to definite outcomes in the physical world also play a role in the processes that give rise to definite experiences? In this framing, consciousness is not an external force acting on physics. It is a phenomenon that may emerge at the same conceptual boundary, where physics itself transitions from possibility to actuality. This idea does not claim certainty. It does not propose a finished theory. It simply notices a pattern. Both quantum physics and conscious experience resist being described as collections of fully defined parts. Both involve contexts, relationships, and transitions. Both challenge the idea that reality is always composed of fixed, observer-independent facts. For some scientists, this resemblance is coincidence. For others, it is a clue. And for many, it is a reminder of how much remains unknown. As these thoughts settle, the story reaches a turning point. We are no longer asking whether consciousness matters to physics. We are asking whether the same unfinished edges in our understanding of reality might also be the place where experience quietly arises. With that question in mind, the narrative begins to narrow toward a specific proposal, one that does not rely on observers or minds as magical ingredients, but instead looks for a physical process that could bridge the gap between possibility and presence from the inside. As the questions around measurement and experience continue to hover, the story now turns toward an idea that emerged not from one field, but from the meeting point of two very different ways of thinking about reality. On one side was a mathematical physicist deeply concerned with the foundations of the universe. On the other was an anesthesiologist working every day with a strange ability to turn consciousness off and on. Each was approaching the mystery from a different direction, yet both were circling the same unresolved gap. The physicist was Roger Penrose, known for his work on space, time, and gravity. Penrose had long been uneasy with the idea that the human mind could be fully explained as a classical computer made of neurons firing in predictable ways. To him, something about human understanding seemed to exceed what ordinary computation could achieve. Penrose did not argue this from intuition alone. He pointed to limits in formal systems, places where mathematical truth cannot be reduced to mechanical rule-following. While these arguments remained debated, they led him to a provocative suspicion. Perhaps human consciousness involves physical processes that are not fully captured by classical physics. At the same time, in a very different corner of science, Stuart Hameroff was grappling with a practical mystery. In operating rooms, he saw patients lose consciousness completely under anesthesia. Not gradually, not fuzzily, but cleanly. Awareness would disappear, even while much of the brain's electrical activity continued. This raised a puzzling question. If consciousness was simply the result of neurons firing and communicating, why could it be shut off so decisively, while many neural processes remained intact? Hameroff noticed something else. Many anesthetic drugs seem to act not primarily on the spaces between neurons, where chemical messages pass, but on structures inside the neurons themselves. These structures were called microtubules, tiny cylindrical scaffolds that help maintain the shape and internal organization of cells. To most neuroscientists, microtubules were housekeeping components, structural support, nothing more. But Hameroff wondered whether this assumption was too narrow. When Penrose and Hameroff began to talk, they found that their questions unexpectedly aligned. Penrose was searching for a physical process that could connect quantum indeterminacy with moments of conscious insight. Hameroff was searching for a biological structure that could plausibly host such a process inside the brain. The result of their collaboration became known as the Orch-OR theory, short for orchestrated objective reduction. The name sounds technical, but its core idea can be described more gently. The proposal suggests that consciousness arises from orchestrated events inside microtubules, where quantum processes unfold and then resolve into definite outcomes. Each resolution corresponds to a tiny moment of experience. Many such moments, organized and coordinated, give rise to the flow of conscious awareness we recognize as a mind. The word orchestrated matters here. It implies coordination, timing, and structure rather than random activity. Just as a symphony is not a collection of isolated sounds, conscious experience, in this view, is not a chaotic blur of quantum noise. The phrase objective reduction refers to a specific idea proposed by Penrose. He suggested that quantum superpositions do not last forever. Instead, when they reach a certain threshold, related to the structure of space and time itself, they become unstable and resolve into a single outcome. This resolution is not caused by observation or awareness. It is a natural physical process built into the fabric of reality. In other words, collapse happens not because something is watching, but because nature imposes limits on how much uncertainty can persist. In the Orch-OR framework, microtubules provide a place where such quantum superpositions might form and evolve in a protected, organized way. When these superpositions reach their natural limit, they undergo objective reduction, producing discrete moments of experience. This is a bold idea, and it is important to approach it with care. Orch-OR does not claim that consciousness floats free of the brain. It does not suggest that thoughts rearrange particles at will. It does not invoke mystical forces or hidden energies. Instead, it places consciousness firmly inside physical processes, while proposing that those processes involve physics that has not yet been fully integrated into neuroscience. One of the most intriguing aspects of this proposal is its treatment of time. According to Orch-OR, consciousness is not a continuous stream, but a rapid sequence of events. Each moment of awareness corresponds to a physical process reaching resolution. Our sense of continuity in this view is a construction. The brain stitches together countless brief moments into the seamless flow we experience as waking life. Much like frames in a film appear as smooth motion when played quickly enough, this idea resonates with everyday experience in subtle ways. Under anesthesia, consciousness does not feel slowed or blurred, it simply disappears. When it returns, there is no sense of time passing in between. One moment you're counting backward, the next moment you're waking up. For Hameroff, this fit what he saw clinically. For Penrose, it fit his view of how quantum processes might connect to moments of understanding. Of course, proposing a connection does not make it true. Many scientists remain skeptical, and rightly so. The brain is warm, noisy, and chemically active. Quantum effects are often fragile. Critics argue that any delicate quantum states inside neurons would be destroyed almost instantly. Penrose and Hameroff responded by pointing to growing evidence that quantum effects can persist in biological systems under the right conditions. Photosynthesis, bird navigation, and enzyme reactions all show signs of quantum coherence in environments once thought too chaotic for such behaviour. This does not prove Orch-OR, it merely keeps the door open. At this stage in the story, it is best to think of Orch-OR not as a final answer, but as a structured question, a framework that attempts to bridge physics and biology without abandoning rigour on either side. Whether it succeeds remains uncertain, but it has done something important. It has shifted the conversation from vague speculation to concrete proposals that can, at least in principle, be tested and refined. As the idea settles, the narrative begins to move inward, toward the structures inside neurons themselves, and toward the question of whether these tiny components might play a role far more profound than anyone once imagined. To understand why microtubules became central to the Orch-OR proposal, it helps to take a slow, careful look inside a single neuron, not as a diagram in a textbook, but as a living, working structure. A neuron is often described as a wire. Signals arrive at one end, travel down a long extension, and trigger chemical messages at the other end. This picture is useful but incomplete. Inside that wire is a dense and dynamic interior, filled with scaffolding, transport systems, and molecular machinery that never appears on the simplified diagrams. Among these internal structures are microtubules. Microtubules are tiny cylindrical tubes, far thinner than anything we could see with an ordinary microscope. They run through neurons like a lattice of support beams inside a building. Their most familiar role is structural. They help cells maintain their shape. They act as tracks along which materials are transported. They are essential for life at the cellular level. For a long time, that was where the story ended. Microtubules were considered passive. Important, yes, but not interesting in the way neurons, synapses, or electrical signals were interesting. Consciousness, after all, was thought to arise from networks of neurons talking to one another, not from the scaffolding inside each cell. What Hameroff noticed, however, was that this assumption rested more on habit than on evidence. Microtubules are not rigid pipes. They are made of repeating protein units arranged in a precise geometric pattern. These proteins can exist in slightly different shapes, and those shapes can influence how the microtubule behaves. In other words, microtubules are not static supports. They are dynamic systems capable of changing state. This matters because information, at its most basic level, is about differences. A switch is meaningful because it can be on or off. A letter is meaningful because it is not another letter. If a physical structure can exist in multiple states, it can, in principle, carry information. Hameroff proposed that microtubulars might be doing just that, not by sending electrical spikes like neurons do, but by shifting patterns internally. Subtle changes in protein configuration could represent bits of information. Large numbers of these bits, coordinated across many microtubules, could form complex patterns. At this point, the idea still sounds classical. Proteins change shape. Information is processed. Nothing especially quantum yet. The quantum step comes from the proposal that some of these protein states might not be fully definite. Instead of being strictly in one configuration or another, they might briefly exist in a spread of possibilities, similar to the superposition we discussed earlier. Again, it helps to soften the language. Imagine a set of wind chimes hanging in still air. Each chime has a natural resting position, but in a gentle breeze, their positions are not fixed. They sway, influence one another, and form patterns of motion that are not easily reduced to a single static arrangement. In the Orch-OR picture, microtubules are not rigid frameworks but sensitive structures, capable of supporting subtle patterns that unfold over very short timescales. These patterns are not random. They're shaped by the surrounding cellular environment, by chemistry, by temperature, and by the larger activity of the neuron. Critics often point out that the brain is warm, wet, and noisy. Quantum effects, they argue, are fragile and easily destroyed under such conditions. This is a serious concern and it cannot be dismissed lightly. Hameroff and Penrose respond by pointing to growing evidence from quantum biology. In recent years, researchers have discovered that certain biological systems can maintain quantum coherence, a kind of coordinated possibility, long enough to be useful. Photosynthetic organisms, for example, appear to use quantum effects to move energy efficiently. Some animals seem to rely on quantum sensitivity to navigate Earth's magnetic field. These systems are not isolated in pristine laboratories. They operate in warm, complex biological environments. This suggests that nature may have found ways to protect delicate processes through structure and organization. In this view, microtubules are not fragile accidents. They are highly ordered arrangements shaped by evolution. Their geometry may help shield and coordinate internal states, allowing subtle effects to persist just long enough to matter. Another intriguing feature of microtubules is their ubiquity. They are found in nearly all cells, not just neurons. This has led to an important clarification. Orch-OR does not claim that microtubules automatically produce consciousness. Structure alone is not enough. What matters is orchestration, the coordination of microtubule activity within the context of neural networks, sensory input, and memory. A single violin string does not create a symphony. An orchestra requires timing, interaction, and direction. In the brain, neurons provide that direction. Synapses shape communication. Electrical rhythms synchronize activity across regions. Microtubules, in this picture, operate within that larger framework, contributing a layer of processing that is invisible at the level of spikes and signals. One of the most important aspects of this proposal is that it does not replace neuroscience. It adds to it. Neurons still fire, networks still form, learning still reshapes connections. Orch-OR suggests that beneath these familiar processes, there may be another layer, one concerned not with transmitting signals, but with integrating them into moments of experience. If this sounds speculative, that is because it is. But it is not arbitrary. The proposal makes specific claims about where consciousness might arise, how it might unfold in time, and why certain interventions, such as anesthesia, can so cleanly disrupt awareness without shutting down the brain entirely. Microtubules are known to be affected by anesthetic molecules. These molecules do not simply silence neurons. They appear to interfere with internal cellular processes. This fits the observation that consciousness can vanish, while much of the brain's activity continues. It also fits the idea that consciousness is not a gradual dimming, but a switch-like transition. One moment there is experience, the next there is none. As these pieces come together, the microtubule shifts from background support to potential participant, not as the sole cause of consciousness, but as part of a multi-layered system where biology, physics, and information intersect. The neuron, once thought of as a simple wire, becomes something richer, a dynamic environment where structure, timing, and subtle internal patterns may contribute to the emergence of awareness. And as we linger with that image, the story prepares to move from structure to time, from the architecture inside neurons to the question of how conscious moments unfold, one after another, creating the seamless flow we call experience. If microtubules provide a possible stage for subtle physical processes, the next question becomes one of time, not clock time, measured in seconds and minutes, but experiential time. The way consciousness feels continuous, even though so much in the brain happens in brief fleeting events. We tend to think of consciousness as a smooth stream, a flowing river of awareness that carries sights, sounds, thoughts, and emotions along with it. This intuition is so strong that it's easy to forget how much of our mental life actually happens in bursts. Neurons fire in spikes, electrical rhythms rise and fall, attention flickers, thoughts appear, dissolve, and are replaced. Even perception, when studied closely, turns out not to be a continuous recording of the world, but a rapid sampling stitched together into something that feels seamless. The Orch-OR proposal leans into this discontinuity. According to this view, consciousness is not a steady glow that stays on all the time. Instead, it is made of countless brief events, tiny moments in which physical processes resolve into something definite. Each of these moments is like a point of clarity, a spark of awareness. When they occur rapidly enough and in an organized way, they create the illusion of a continuous experience. To soften this idea, it helps to think about film. A movie feels like smooth motion, but it is actually a sequence of still frames shown in rapid succession. Each frame is static, yet when played quickly enough, the brain blends them into a flowing scene. The continuity is real as an experience, even though it is built from discrete pieces. In the Orch-OR framework, conscious moments are like those frames. Each moment arises when a quantum process inside microtubules reaches a natural limit and resolves. This resolution is not triggered by observation or choice. It happens because the physical system can no longer sustain multiple possibilities at once. When that resolution occurs, a moment of experience emerges. This does not mean that each moment is rich or complex on its own. Many moments may be simple, carrying only faint impressions or background awareness. Others, shaped by attention and neural coordination, may be vivid and detailed. What matters is not the content of a single moment, but the way many moments are organized over time. This idea helps explain something that has puzzled both scientists and clinicians for a long time. When consciousness disappears, under anesthesia for example, it does not fade slowly. There is no sense of time stretching or awareness dimming into darkness. One moment you are aware, the next moment awareness is gone, and when it returns there is no memory of time passing in between. From the Orch-OR perspective, this makes sense. If consciousness depends on a sequence of discrete events, then interrupting the physical conditions that allow those events to occur would stop the sequence entirely. There would be no moments to experience time and therefore no sense of duration. Sleep offers a gentler example. As you drift into deep sleep, awareness fragments, thoughts become less coherent, sensations fade, the sequence of conscious moments slows and becomes less organized. Eventually, it stops producing anything that registers as experience, and yet, when you wake, consciousness does not need to be rebuilt from scratch. The underlying structures are still there. The conditions simply shift back into a regime where moments of awareness can occur again. This view also casts new light on the feeling of nowness that accompanies experience. Each conscious moment feels like a present instant, complete in itself. The sense of past and future arises from memory and anticipation, not from the moment itself. If consciousness is indeed composed of discrete events, then the present is not a slice of a continuous timeline. It is a recurring arrival point, appearing again and again as physical processes resolve. This may help explain why the present moment feels so different from remembered or imagined ones. Memory involves reconstructing past patterns. Imagination involves projecting possibilities. But the present involves a physical process reaching completion. Of course, this raises an immediate concern. If consciousness comes in discrete moments, how short are they? How many occur each second? The Orch-OR proposal suggests that these moments are extremely brief, far shorter than anything we consciously notice. Their exaggeration depends on the physical details of the processes involved. Here, it is important to avoid getting lost in numbers or symbols. The key idea is not the precise timing, but the principle. Consciousness, in this view, is event-based rather than substance-based. It happens rather than simply existing. This framing also helps clarify why consciousness feels unified rather than fragmented. The brain does not experience isolated moments in chaos. Neural activity coordinates which microtubule processes contribute to experience at any given time. Attention, memory, and sensory input shape which moments are emphasized and which fade into the background. In other words, orchestration matters. Without coordination, discrete events would remain isolated sparks. With coordination, they form patterns, and with patterns, meaning emerges. Critics often worry that this picture reduces consciousness to something mechanical, but that concern may come from imagining these moments as switches flipping on and off. The reality, if this theory is correct, would be far more subtle. Each moment would reflect the state of the entire system, the brain, the body, and the environment, integrated into a single event. This is why Orch-OR emphasizes organization over randomness. Consciousness is not produced by isolated quantum collapses happening anywhere in the brain. It arises from collapses that are structured, synchronized, and shaped by biology. Whether this picture is ultimately correct remains an open question, but it offers a way to think about consciousness that aligns with lived experience in an unexpected way. Experience does not feel like a static thing you possess. It feels like something that keeps happening, again and again, moment by moment. As we rest with this idea, it gently reframes the question of continuity. Perhaps consciousness feels continuous not because it is continuous, but because it is renewed so rapidly that gaps never register. And with that reframing in place, the story begins to turn toward the objections, toward the reasons many physicists remain unconvinced that such delicate processes could survive inside the brain at all. As intriguing as the Orch-OR proposal may sound, this is the point where many physicists quietly lean back in their chairs and begin to frown, not because the idea is imaginative, not because it reaches beyond familiar territory, but because it appears to collide head-on with one of the most well-established lessons of quantum physics. Quantum effects, we are told, are fragile. They flourish in carefully controlled environments, in laboratories cooled to near absolute zero, in systems isolated from vibration, heat, and disturbance. Even then, they tend to vanish quickly, washed away by interaction with the surrounding world. The brain, by contrast, is almost the worst possible place to look for delicate quantum behavior. It is warm, it is wet, It is chemically active. It is constantly buzzing with electrical signals. From a physicist's point of view, the brain looks like a stormy ocean, not a quiet pond. And quantum coherence, the coordinated behavior of multiple possibilities, is thought to dissolve rapidly in such conditions. This objection has a name: decoherence. Decoherence describes the process by which quantum possibilities lose their ability to interfere with one another. As a system interacts with its environment, its subtle quantum structure becomes scrambled. The system no longer behaves as a unified set of possibilities, but as an ordinary classical object with definite properties. In simple terms, decoherence is what makes the world look solid and predictable, instead of ghostly and blurred. One physicist who examined this issue closely was Max Tegmark. He asked a straightforward question: if quantum states were involved in brain function, how long could they realistically survive? Using estimates based on temperature, mass, and interaction strength, Tegmark concluded that any quantum coherence in the brain would vanish almost instantly, far faster than the timescales associated with neural processing or conscious thought. The conclusion seemed devastating. If quantum states collapse into classical noise almost immediately, then they cannot play any meaningful role in cognition or awareness. The brain, in this view, is simply too hot and too busy for quantum subtlety. This critique matters. It is not a casual dismissal. It comes from well-tested physical principles and careful reasoning. Any theory that claims quantum involvement in consciousness must take this objection seriously. And yet, this is not where the discussion ends. To understand why, it helps to look more closely at what decoherence actually says and what it does not say. Decoherence does not forbid quantum effects in warm environments. It says that unprotected quantum states tend to lose coherence quickly when they interact randomly with their surroundings. But this leaves open an important possibility. What if a system is structured in such a way that interaction is not random? In recent decades, physicists and biologists have begun to discover examples of quantum effects persisting in places they were once thought impossible. Photosynthetic complexes, for instance, appear to guide energy efficiently using quantum coordination. Certain animals seem to exploit quantum sensitivity to detect magnetic fields. Enzymes may use quantum tunneling to speed up chemical reactions. These systems do not isolate themselves from their environment. Instead, they are organized in ways that channel interaction rather than letting it dissolve into noise. This distinction is crucial. Noise destroys coherence when it is uncontrolled. Structure can preserve coherence by shaping how interactions occur. Penrose and Hameroff argue that microtubules may belong to this second category, not as fragile quantum toys, but as highly ordered biological structures evolved to manage internal dynamics with precision. Their proposal does not require long-lasting quantum states drifting freely inside neurons. It requires brief, orchestrated processes that unfold quickly and then resolve. In other words, coherence does not need to persist indefinitely. It only needs to last long enough to contribute to a moment of experience. Think of a ripple on water. It does not last forever. It does not need to. It only needs to exist long enough to carry information from one place to another. From this perspective, Tegmark's calculations do not end the conversation. They define the challenge. They tell us what must be explained, not what is impossible. Critics often assume that Orch-OR depends on large, isolated quantum superpositions behaving like those in physics experiments. But the proposal is subtler than that. It suggests that biological systems may operate at the edge between quantum and classical behavior, using brief coherence events that are rapidly resolved. This does not make the idea correct, but it does mean that dismissing it requires more than pointing out that the brain is warm. Another important clarification is that decoherence explains why quantum behavior becomes unobservable at large scales. It explains why we do not see superpositions of everyday objects, but it does not explain why one specific outcome is experienced rather than another. In other words, decoherence explains the disappearance of interference, not the selection of experience. This distinction often gets blurred in popular discussions. It is easy to think that once decoherence happens, the problem is solved. But from the perspective of conscious experience, something remains unexplained. Why this outcome, here, now? For physicists focused on prediction and measurement, this question may feel unnecessary. The equations work, experiments agree. Why worry about experience? For those concerned with consciousness, however, this question sits at the centre of the mystery. The hard problem has not vanished. It has simply moved. This is why Orch-OR continues to provoke discomfort. It does not deny decoherence. It does not reject physics. Instead, it suggests that the transition from quantum possibility to classical reality may be more than a bookkeeping device. It may be connected to how definite experience arises. This suggestion unsettles many physicists because it blurs a boundary they prefer to keep sharp. The boundary between physical description and lived reality. To be clear, skepticism here is healthy. Extraordinary claims require extraordinary evidence. Orch-OR remains controversial, and many researchers remain unconvinced that microtubules can support the processes it proposes. But controversy alone does not invalidate a question. Science advances not only by solving problems, but by identifying where existing explanations feel incomplete. The warm, noisy brain problem marks such a place. It forces theorists to be precise, cautious, and creative. As we sit with this objection, it is worth noticing what it accomplishes. It does not shut the door on quantum consciousness. It does not prove it correct. It sharpens the question. If quantum processes play a role in consciousness, they must do so in a way that respects the messy, dynamic nature of biology. They must be brief, structured, and integrated into larger systems. Whether such processes exist remains to be seen. But the discomfort they provoke serves an important function. It keeps the discussion grounded. It prevents speculation from drifting too far from physical reality. And as the story continues, the focus shifts toward a key clarification. That Orch-OR does not depend on observers or minds collapsing reality, but on a different idea entirely. One that brings gravity, structure, and physical limits into the picture. Once the concern about a warm, noisy brain has been carefully set on the table, another confusion often follows close behind it. A confusion so persistent that it has shaped decades of misunderstanding. If quantum collapse is involved in consciousness, does that mean a conscious observer is required for reality to exist? This idea has a long history, and it is one of the main reasons many physicists instinctively recoil when consciousness enters a discussion about quantum mechanics. The image is an uncomfortable one. Particles waiting in limbo until a mind looks at them. The universe somehow incomplete without awareness. It is important to say this clearly and calmly. That is not what the Orch-OR proposal claims. To see why, we need to gently separate two very different ideas that are often tangled together: observer-based collapse and objective reduction. In early interpretations of quantum mechanics, measurement was closely associated with observation. A physicist looked at a detector, a result appeared. It was tempting to think that awareness itself was doing something special. But this was never a satisfying explanation. It simply pushed the mystery into the mind without explaining how or why. Penrose took a different route. Rather than asking what the observer does, he asked what nature does. He proposed that quantum superpositions are not infinitely stable. They do not linger forever waiting to be noticed. Instead, they have a natural limit, When a superposition becomes too large or too complex, it becomes unstable and resolves into a single outcome on its own. This process is what he called objective reduction. The word objective matters. It means that the process does not depend on anyone watching. It is built into the physical structure of reality itself. Collapse, in this view, is not triggered by observation. It is triggered by physical conditions. To make this idea more intuitive, imagine trying to balance a pencil perfectly upright on its tip. For a moment it might stay balanced, but as time passes, tiny disturbances accumulate. The pencil wobbles, and eventually it falls in one direction. Not because someone chose that direction, but because perfect balance is unstable. The fall is inevitable, even if unpredictable. In Penrose's picture, quantum superpositions are a bit like that balanced pencil. They can exist for a time, but only up to a point. When they cross a certain threshold, they resolve into a definite state. What sets that threshold? This is where gravity enters the story. Gravity in everyday life feels gentle and continuous, but at a fundamental level, it interacts with mass and energy in a way that shapes the structure of space and time itself. Penrose suggested that when a quantum system involves significantly different mass distributions at once, it creates a kind of tension in space-time. That tension cannot be sustained indefinitely. Rather than describing this with equations or symbols, it is easier to think in terms of strain. Imagine stretching a rubber sheet in two incompatible ways at the same time. For a moment the sheet can accommodate the conflict, but beyond a certain point, it must snap into one configuration or the other. Objective reduction in this view is the snapping. No observer is required, no awareness intervenes. Nature simply enforces a limit on how much ambiguity it can tolerate. This distinction is crucial because it removes one of the most troubling implications people often associate with quantum consciousness. Orch-OR does not claim that minds create reality by looking at it. It claims that reality has built-in mechanisms for becoming definite. Where consciousness enters the picture is not as a cause of collapse, but as a phenomenon that may be associated with these collapse events when they occur in highly organized biological structures. In other words, consciousness does not collapse wave functions. Collapse may produce moments of consciousness when it happens in the right context. This framing restores scientific grounding. It keeps physics doing what physics does best, describing natural processes without reference to subjective experience. At the same time, it allows for the possibility that subjective experience arises from those processes under special conditions. Physicists are still uneasy with this idea, and their unease is understandable. Gravity is the least understood of the fundamental interactions at the quantum level. We do not yet have a complete theory that unites gravity with quantum mechanics. To suggest that consciousness depends on physics we do not fully understand feels premature. But Penrose's proposal does not pretend to close that gap. It highlights it. If objective reduction is real, it would point toward a deeper layer of physical law, one where quantum theory and gravity meet. Consciousness, in this view, would not be an anomaly added to physics. It would be a clue pointing toward its unfinished foundations. This is a delicate position to hold. Too cautious, and nothing new is said. Too bold, and speculation outruns evidence. Orch-OR tries to walk the narrow path between these extremes. It does not deny the success of existing physics. It does not claim experimental confirmation. It simply suggests that the unresolved questions at the heart of quantum theory may be relevant to the unresolved questions at the heart of consciousness. This suggestion alone is enough to make many physicists uncomfortable. Physics has progressed, in part, by deliberately excluding subjective experience from its explanations. Introducing consciousness, even indirectly, feels like reopening a door that was carefully closed. Yet, The door may never have been fully sealed. The measurement problem remains. The nature of collapse remains unsettled. The relationship between physical description and experienced reality remains unexplained. In that sense, Orch-OR does not invent a new mystery. It connects two existing ones. As this clarification settles, the emotional tone of the debate begins to shift. The concern is no longer about mystical observers or minds shaping the universe. It is about whether the boundaries between physical processes and experiential ones are as clean as we would like them to be. And with that grounding restored, the story moves toward another misunderstanding that often clouds discussions of quantum consciousness. The fear that if quantum effects are involved, then minds must somehow merge, overlap, or become indistinct. That, too, is not the claim. As the discussion moves deeper into quantum territory, a familiar phrase often drifts in from the edges of popular culture, a phrase that sounds comforting, poetic, and faintly mystical. We are all connected. When quantum physics and consciousness appear in the same sentence, this idea almost seems inevitable. Entanglement, after all, is real. Particles can share relationships that persist across distance. Measurements on one can be correlated with measurements on another in ways that defy classical intuition. It is tempting to extend this strangeness directly to the mind. If particles can be linked, perhaps minds are linked too. If quantum effects are involved in consciousness, perhaps individuality dissolves. Perhaps boundaries between selves are not as real as they feel. This line of thinking is one of the reasons many physicists become uneasy. Not because entanglement is false, but because it is often misunderstood. To see why, it helps to slow down and carefully unpack what entanglement actually means, and just as importantly, what it does not mean. Entanglement occurs when two or more particles are described by a shared physical state. Their properties are correlated in such a way that measuring one provides information about the other. This correlation can persist even when the particles are far apart. What makes entanglement remarkable is not that information travels faster than light. It does not. No usable signal is sent. No message is transmitted. Entanglement does not allow communication, control, or influence across distance. Instead, it reflects a shared history. A simple analogy helps soften this idea. Imagine two gloves placed into separate boxes. One glove is left-handed, the other right-handed. If you open one box and find a left glove, you immediately know the other box contains a right glove. No signal was sent between the boxes. The information was already encoded in the pair. Quantum entanglement is subtler than this, but the key point remains. Correlation does not imply communication. This distinction is critical when it comes to consciousness. Orch-OR does not claim that minds are entangled with one another. It does not suggest that thoughts leak between people or that individuality dissolves at the quantum level. There is no mechanism in the theory for mind-reading, shared awareness, or collective consciousness. The quantum processes proposed in Orch-OR are local. They occur inside microtubules within individual neurons. They are shaped by the structure of a single brain, influenced by that brain's history, biology, and sensory input. Even if quantum coherence plays a role, it does so within strict boundaries. Those boundaries matter. A conscious experience is not just a physical event, it is an organized event. It depends on memory, perception, bodily state, and context. These are not shared between brains. They are built through development, learning, and personal history. Entanglement does not erase these structures. It does not blur them together. Physics offers no pathway by which quantum correlations could override the layered organization that makes each mind distinct. So why does the unease persist? Part of the answer lies not in physics, but in language. Words like connected, non-local, and shared carry emotional weight. They invite metaphors that stretch beyond what the science actually supports. When these metaphors are applied too freely, they create the impression that quantum theory dissolves individuality itself. Physicists are wary of this slide because it replaces careful explanation with suggestion. It turns precise phenomena into vague symbolism. Another source of discomfort is more subtle. Even when entanglement is understood correctly, it still challenges classical intuitions about separateness. It suggests that some aspects of reality cannot be fully described by looking at parts in isolation. Relationships matter, context matters. For scientists trained to analyze systems by breaking them into independent components, this is deeply unsettling. Now imagine adding consciousness to the mix. Consciousness already resists reduction. It already feels holistic. It already blurs the line between subject and object. When quantum concepts are introduced, it can feel as though the remaining boundaries are under threat. But Orch-OR does not erase boundaries. It relocates the mystery. Instead of asking how minds connect to each other, it asks how physical processes connect to experience. The question is not whether we are all one mind, but how any mind arises at all. This is a crucial shift. By keeping quantum processes local and structured, Orch-OR avoids the most extravagant interpretations. It does not claim that consciousness is a universal field. It does not claim that awareness floats freely through space. It does not claim that identity is an illusion. In fact, it does the opposite. It emphasizes organization, containment, and specificity. Consciousness, in this view, is something that happens when physical processes are arranged in a particular way, within a particular system. Each brain is its own stage. Each life writes its own script. So why do physicists still feel uneasy? Because even this restrained proposal pushes against a long-standing methodological boundary. Physics has succeeded by describing the world in ways that do not depend on who is experiencing it. Introducing consciousness, even indirectly, risks complicating that separation. There's also a fear of misinterpretation. Once quantum language enters discussions of mind, it can easily be co-opted into claims that are unfalsifiable, untestable, or simply wrong. Physicists worry, not unreasonably, about their work being used to justify ideas they do not support. This tension is not unique to Orch-OR. It appears whenever deep scientific ideas cross into questions of meaning and experience. The solution is not to avoid the questions, but to approach them with care. Orch-OR, at its best, does not promise cosmic unity or hidden connections between minds. It offers a disciplined attempt to explore whether the unresolved edges of physics might illuminate the unresolved edges of consciousness. That exploration may ultimately fail. The theory may be revised, replaced, or abandoned, but it is not a claim that we are all the same mind, whispering to each other across the universe. It is a claim that the processes giving rise to experience may be more subtle than we once assumed. As this clarification settles, the tone of the story begins to soften again. The sharp edges of controversy give way to something quieter, a return to biology, to experiments, to hints rather than declarations. The next step is not philosophical, it is practical. If consciousness can be turned off so cleanly, so reliably and so reversibly, then perhaps that switch can teach us something about where consciousness actually lives. After long debates about theory, interpretation, and discomfort, the story now turns towards something surprisingly concrete. Not an equation, not a philosophical puzzle, but a routine medical practice that millions of people experience every year: anesthesia. Few things illustrate the mystery of consciousness more vividly than the way anesthesia works. Not because it puts the brain to sleep, but because it does something far stranger. It turns experience off. When a person is anesthetized, their brain does not shut down. Electrical activity continues. Blood flows, neurons fire, reflexes may persist. The machinery of life keeps running. And yet consciousness disappears. There is no gradual fading into darkness, no awareness of time stretching thin. One moment you are aware, the next there is nothing. When awareness returns, it feels as though no time has passed at all. This clean binary quality has puzzled scientists for decades. Sleep, by contrast, is messy. It drifts, it fluctuates, dreams intrude, awareness waxes and wanes. Anesthesia does none of this. It produces a sharp boundary between experience and non-experience. This alone makes anesthesia a powerful lens for studying consciousness. If consciousness was simply the sum of neural firing, one might expect anesthesia to gradually dampen activity until experience slowly dissolves. But that is not what happens. Much of the brain remains active, yet experience vanishes completely. This suggests that consciousness depends not just on activity, but on a specific kind of organization. From the Orch-OR perspective, anesthesia becomes especially interesting. Many anesthetic molecules are chemically simple. They are small, inert, and unreactive. They do not dramatically alter brain chemistry. Instead, they subtly bind to structures within neurons. Over time, evidence has accumulated that anesthetics interact with microtubules. They appear to interfere with internal cellular processes rather than shutting down communication between neurons entirely. This is a crucial distinction. If consciousness arises from processes happening between neurons, anesthesia should primarily disrupt synapses. If consciousness arises from processes happening within neurons, anesthesia would be expected to act internally. What we observe leans toward the second picture. Under anesthesia, neurons can still communicate. Brain rhythms continue. Sensory signals may still be processed at early stages. But the integration that gives rise to experience fails. From the Orch-OR viewpoint, this makes sense. If consciousness depends on orchestrated events inside microtubules, then disrupting those events would stop conscious moments from forming, even while the rest of the brain remains active. Think of a factory where the lights are still on and machines are still humming, but the final assembly step has been disabled. Parts move, signals pass, but the finished product never appears. Anesthesia may be interrupting that final step. Another striking feature of anesthesia is reversibility. When the drug wears off, consciousness returns, memories resume, identity feels intact. There is no sense of having been partially conscious during the gap. This all-or-nothing quality fits poorly with theories that treat consciousness as a gradual emergent property of neural activity. But it fits naturally with theories that treat consciousness as a sequence of discrete events. If the physical conditions for those events are disrupted, the sequence stops. When the conditions return, the sequence resumes. Anesthesiologists have long known that different drugs can produce similar loss of consciousness through different mechanisms. This suggests that there is more than one way to interrupt the process, but the outcome remains remarkably consistent. Experience disappears. From a scientific perspective, anesthesia functions as a kind of controlled experiment. We can reliably turn consciousness off and on without destroying the brain. That alone tells us that consciousness is not a diffuse property smeared across all neural activity. It is localized in function, if not in space. This insight has implications beyond Orch-OR. Even scientists who reject quantum involvement acknowledge that anesthesia reveals a deep separation between neural processing and conscious experience. There is processing without awareness, there is activity without experience, the hard problem does not go away. For supporters of Orch-OR, anesthesia becomes an intuition pump rather than a proof. It suggests where to look. It highlights internal cellular structures as potential sites of disruption. It aligns with the idea that consciousness depends on fine-grained organization rather than sheer activity. Critics rightly point out that correlation is not causation. Just because anesthetics affect microtubules does not mean microtubules produce consciousness. Anesthetics interact with many targets in the brain. This caution is important. But the fact remains that anesthesia challenges simplistic models. It forces us to ask not how the brain processes information, but how experience arises from that processing in the first place. Why does experience vanish when certain internal processes are disrupted, even while the brain remains active? This question does not require quantum theory to be meaningful. But quantum theory offers one possible framework for thinking about it. In that framework, consciousness depends on processes that are both delicate and organized. Processes that can be interrupted without silencing the entire system. Processes that give rise to moments of awareness rather than continuous glow. From this angle, anesthesia looks less like sleep and more like a switch, a precise interruption of the conditions required for experience. That precision is what makes it scientifically valuable. As research continues, anesthetics may help narrow the search for consciousness's physical correlates, not by offering mystical insights, but by providing reproducible, reversible, and clinically relevant data. Whether Orch-OR ultimately explains these effects remains uncertain, but anesthesia ensures that the mystery stays grounded. It keeps the discussion tied to biology, medicine, and lived experience, and as the narrative continues, it moves from this clinical switch to a stranger and more unexpected clue. A puzzle involving atoms that are chemically identical, yet behave differently in ways that may hint at deeper physical layers beneath consciousness itself. As anesthesia continues to serve as a clean switch for consciousness, one particular line of research introduces a detail so subtle that it almost feels accidental. And yet this detail is proven difficult to ignore. It involves xenon. Xenon is a noble gas. It is chemically inert, meaning it does not readily react with other substances. Because of this, xenon has been used as an anesthetic in both clinical and experimental settings. Its effects are reliable, reversible, and relatively gentle on the body. At first glance, xenon seems unremarkable, but when researchers began comparing different forms of xenon, something unexpected emerged. Atoms of xenon can exist in multiple isotopic forms. These isotopes are chemically identical. They behave the same way in reactions. They bind to the same places. From a classical chemical perspective, there should be no meaningful difference between them. And yet, experiments showed that different xenon isotopes produced different anesthetic effects. This result was surprising precisely because it violated expectations. If anesthesia worked purely through classical chemistry, isotopes should behave the same way. Chemistry depends on electron structure, not on subtle nuclear properties, but isotopes differ not in their electrons, but in their nuclei. This points towards something deeper. One of the key differences between xenon isotopes lies in a property called spin. Rather than thinking of spin as literal rotation, it is better to imagine it as a built-in orientation, a tiny internal compass that gives the nucleus a kind of directional character. Some xenon isotopes have nuclear spin, others do not. When researchers compared these isotopes, they found that those with nuclear spin produced measurably different anesthetic effects than those without it. The chemistry was the same, the binding sites were the same, only the quantum property differed. This does not prove that consciousness is quantum, but it raises a difficult question. Why should nuclear spin matter at all? Spin is a quantum property. It does not have a classical analogue. Its influence suggests that the anesthetic effect may depend on more than just chemical binding. It may involve interactions sensitive to quantum-level features. From the Orch-OR perspective, this result is intriguing because microtubules contain networks of aromatic molecules that may be sensitive to such properties. If anesthetics disrupt subtle internal dynamics rather than gross neural activity, then differences in quantum properties could plausibly matter. Again, it is important to move carefully. These experiments do not show that nuclear spin creates or destroys consciousness. They do not show that microtubules are the sole target. They do not rule out alternative explanations. What they do show is that the anesthetic effect is not fully explained by classical chemistry alone. For many physicists and neuroscientists, this is unsettling. It suggests that the mechanism by which consciousness is suppressed may reach deeper than expected, not into mysticism, but into physics that is still being actively explored. One way to think about this is through resonance. Imagine two tuning forks placed near each other. Strike one, and the other may begin to vibrate if they share the right frequency. The interaction depends not just on contact, but on internal structure. In a similar way, anesthetic molecules may interact with internal cellular processes in ways that depend on subtle properties like spin. The interaction is not brute force disruption, it is selective interference. This helps explain why anesthesia can be so precise. Consciousness disappears, but much of the brain continues to function. Memory formation may pause, but reflexes remain. Vital systems stay online. The effect is targeted, not global. The xenon isotope findings fit this pattern. They suggest that consciousness depends on processes that are sensitive to fine-grained physical details. Processes that can be disrupted without dismantling the entire system. Critics rightly emphasize that these results are not conclusive. The experiments are complex. Replication and refinement are ongoing. Alternative interpretations remain possible. This caution is essential. Science advances not by seizing on anomalies as proof, but by treating them as questions. The xenon isotope mystery is valuable precisely because it resists easy explanation. It invites deeper investigation into where anesthesia acts and why. It also highlights a broader theme that runs through quantum biology. Nature does not always use blunt instruments. It often exploits subtle physical effects to achieve efficiency and precision. If biological systems already make use of quantum sensitivity in other contexts, then it is not unreasonable to ask whether the brain might do the same. Not everywhere, not all the time, but in specific, highly organized contexts. The xenon experiments do not tell us what consciousness is, but they remind us of what it is not. It is not simply chemical activity. It is not merely electrical signaling. It is not guaranteed by neural firing alone. There is something about the organization of physical processes that matters. This realization does not commit us to Orch-OR. It does not require us to accept microtubules as the seat of experience, but it does weaken the assumption that classical explanations are sufficient by default. For listeners drifting towards sleep, this is perhaps the most important takeaway. The mystery of consciousness persists not because science has failed, but because it keeps uncovering layers where our intuitions break down. Each layer brings us closer to the question, even as it complicates the answer. The xenon isotope mystery is one such layer, a quiet anomaly, a gentle nudge. It does not shout. It does not proclaim truth. It simply refuses to fit neatly into the boxes we expected. And in doing so, it invites us to remain curious rather than certain. As the story continues, it widens its lens once more, away from the brain specifically and toward life itself, toward the growing realization that quantum effects may already be woven into biological systems in ways we're only beginning to understand. After the xenon isotope mystery, it is tempting to think that quantum biology is a fringe idea, hovering at the edges of respectable science, something speculative, fragile, and easily dismissed. But this impression no longer matches reality. Over the past few decades, a quiet shift has taken place. One by one, researchers have uncovered examples of quantum effects operating inside living systems, not in exotic conditions, but in warm, wet, ordinary biological environments. What once seemed impossible has become difficult to ignore. The most well-known example comes from photosynthesis. Plants and certain bacteria capture sunlight and convert it into chemical energy with astonishing efficiency. For a long time, scientists assumed this process was purely classical. Light hits a molecule, energy hops from one place to another, and eventually reaches a reaction center. But closer study revealed something unexpected. Instead of energy moving step by step like a bouncing ball, it appears to explore multiple pathways at once. The system briefly samples different routes and settles on the most efficient one. This behavior is best described not as trial and error, but as coordinated possibility. In other words, quantum coherence. The energy does not wander randomly. It spreads out like a ripple and then converges. This allows the organism to harvest light with minimal loss, even in noisy conditions. Importantly, this coherence does not last long. It does not need to. It exists just long enough to guide the process, and then it disappears. This pattern should sound familiar. It mirrors the kind of short-lived, structured quantum behavior proposed in Orch-OR. Not long-lived superpositions floating freely, but brief, purposeful events embedded in a biological context. Another example comes from animal navigation. Some birds appear to sense Earth's magnetic field in order to orient themselves during migration. Classical explanations struggle to account for the sensitivity of this ability. The magnetic field is weak. The signals are subtle. Quantum biology offered a possible answer. Certain molecules in the bird's retina may exist in a state where their behavior depends on quantum correlations. The orientation of Earth's magnetic field influences how these molecules evolve, subtly affecting vision. The bird does not see magnetic lines. Instead, its visual field is gently modulated in a way that guides navigation. Again, this process does not require isolation or low temperatures. It works precisely because it is integrated into a living system. Enzymes provide yet another example. Many biochemical reactions occur far faster than classical chemistry predicts. Quantum tunneling, where particles cross energy barriers they should not be able to cross, helps explain this speed. Enzymes appear to shape their internal environments to make such tunneling more likely. Life, it seems, is not afraid of quantum weirdness. It uses it when it helps. These discoveries change the tone of the debate. The question is no longer whether quantum effects can exist in biology. They can, and they do. The question is where, how, and to what extent they matter. This matters greatly for discussions of consciousness. For years, critics dismissed quantum mind theories by pointing out that the brain is too warm and noisy. Quantum biology shows that warmth and noise are not automatic deal breakers. Structure matters, organization matters, timing matters. Biological systems do not fight their environments, they work with them. This does not mean that every biological process is quantum. Most are not. It means that evolution has, in some cases, found ways to harness quantum effects where they provide an advantage. If that is true, then it becomes reasonable, not reckless, to ask whether the brain might also exploit such effects in specific contexts. Not everywhere, not continuously, but perhaps in carefully orchestrated ways. This is where Orch-OR fits into the broader landscape. It does not claim that consciousness is the only quantum phenomenon in biology. It places consciousness alongside others as a possible case where quantum effects play a subtle but meaningful role. The proposal suggests that microtubules, with their ordered structures and internal networks, may be capable of supporting brief coherence events. These events would not replace neural activity. They would complement it. Neurons still fire, networks still process information, but beneath that familiar activity, there may be another layer where possibilities briefly coexist before resolving. This layered picture is important. It avoids the mistake of pitting quantum explanations against classical neuroscience. Instead, it suggests that different levels of description may be needed for different aspects of the mind. Memory formation, perception, and learning may be well explained by classical mechanisms. The raw fact of experience, the feeling of being aware at all, may require something additional. Quantum biology does not solve the hard problem, but it shows that nature already uses tools we once thought were off limits to life. That alone is a significant shift. Of course, caution remains essential. Not every quantum effect discovered in biology has proven central or robust. Some findings are debated, others are still being refined. Enthusiasm must be balanced with skepticism, but skepticism cuts both ways. It is no longer reasonable to dismiss quantum involvement in biology as fantasy. The field has matured. It has produced testable hypotheses, experimental data, and practical insights. In that light, Orch-OR looks less like an outlier and more like a bold extension of an emerging paradigm. It may be wrong. Many bold ideas are. But it is not disconnected from the trajectory of science. For a listener easing towards sleep, this realization can feel grounding rather than destabilizing. The universe is not divided into neat categories where quantum physics belongs in one box and life in another. Reality is layered, interconnected, and often more subtle than our first explanation suggests. Life already dances on the edge between order and uncertainty, between stability and change, between classical certainty and quantum possibility. Whether consciousness joins that dance remains an open question, but it is no longer a question that can be dismissed with a wave of the hand. As this part of the story comes to rest, the tone shifts once more, away from mechanisms and experiments and toward meaning. If consciousness is not a thing, but a process, not a substance, but a pattern, then what does that mean for who you are? That question waits quietly, ready to unfold. After travelling through physics, biology, and uncertainty, the story now turns inward, not towards speculation about the universe, but towards something more personal, something quietly familiar, you. If consciousness truly depends on organised processes rather than static substances, then the question of identity begins to shift. Not abruptly, not dramatically, but gently, like a change in lighting that reveals a room differently. Most of us carry an unspoken assumption that the self is a thing, a stable object located somewhere behind the eyes, something that persists unchanged as time passes. But when we look closely, this picture begins to soften. Your body is not the same collection of atoms it was years ago. Cells divide, die, and are replaced. Molecules are exchanged with the environment constantly. Even the structures inside your neurons are in flux, assembling and disassembling as part of normal life. And yet, you remain you. This continuity does not come from material permanence, it comes from pattern. A pattern can persist even as its components change. Think of a river. The water flowing through it today is not the water that flowed yesterday. And yet the river remains recognizable. Its shape, direction, and behaviour endure because the pattern is maintained, not because the material stays the same. In this light, identity looks less like an object and more like an ongoing process. Orch-OR, if it were true, would fit naturally into this view. Consciousness would not be something you have, like a possession. It would be something that keeps happening moment by moment as long as the underlying organisation is maintained. This helps clarify a long-standing puzzle. Why does identity feel continuous even though memory is unreliable? Memories are not stored like files in a cabinet. They are reconstructed. Each time you remember something, the memory is rebuilt from fragments, influenced by your current state. Details shift, emotions change, gaps are filled, and yet memory still contributes to a sense of self. Because identity does not depend on perfect recall. It depends on coherence. The pattern holds even when details blur. From this perspective, consciousness is not the sum of all your thoughts or memories. It is the process by which experience is integrated into a coherent whole. A process that gives rise to a feeling of presence, of being here, now. This view avoids both extremes that often dominate discussions of the self. On one side is the idea of a permanent essence, an unchanging core that defines who you are. On the other side is the idea that the self is an illusion, a story with no grounding at all. A pattern-based view occupies a middle ground. The self is real but dynamic, stable but not fixed, grounded in physical processes but not reducible to any single component. If consciousness arises from organised physical events, then identity is not located in a particular atom, neuron, or microtubule. It is distributed across time, across activity, across structure. This has calming implications. It means that change does not automatically threaten identity. Growth, learning, and adaptation are not losses of self. They are expressions of the same pattern responding to new conditions. It also means that disruption does not necessarily erase identity entirely. During anesthesia, the pattern pauses. Conscious moments stop forming, but the underlying organisation remains intact. When the process resumes, the pattern reappears, and with it the sense of self. This explains why waking from anesthesia feels instantaneous. There is no experience of absence because absence is not something that can be experienced. There is only the presence of the pattern, or its absence. When it returns, it feels continuous. This way of thinking also reframes questions about damage and recovery. Brain injuries, illnesses, and aging can alter the pattern, sometimes subtly, sometimes profoundly. Identity may shift, but it does not vanish simply because components change. What matters is not sameness, but continuity. From a scientific standpoint, this view is modest. It does not invoke souls, hidden essences, or cosmic identities. It stays close to what we can observe: processes, organisation, and change over time. From a human standpoint, it can be quietly reassuring. You're not a fragile object that must be preserved perfectly to exist. You are a living pattern, capable of persistence through change. If Orch-OR were correct, it would add an unexpected layer to this picture. It would suggest that the pattern of consciousness includes moments where physical uncertainty resolves into experience, moments where possibility becomes presence. But even without committing to that theory, the broader idea remains valuable. Consciousness is something that happens. Identity is something that unfolds. This reframing also helps dissolve a common fear, the fear that reducing consciousness to physical processes makes life feel empty or mechanical. In reality, it does the opposite. Patterns can be rich, dynamic, meaningful. A symphony is nothing more than organised sound over time, and yet it can move us deeply. A story is nothing more than arranged words, and yet it can change how we see the world. meaning does not require permanence of parts. It requires coherence of form. As the story prepares to move forward, this perspective sets the stage for one of the most sensitive questions of all. If consciousness is a process shaped by physical law, then what does that mean for choice, agency, and freedom? That question does not demand dramatic answers. It asks for careful ones, and it waits patiently, ready to be explored. Once identity is understood as a pattern rather than a fixed thing, another question naturally follows. A question that has quietly haunted philosophy, science, and everyday life for centuries. If consciousness arises from physical processes, then what becomes of free will? This question often arrives wrapped in extremes. Either we imagine total freedom, a self that floats above physical law and chooses independently of causes, or we imagine total determinism, a universe where every action is the inevitable result of prior conditions, leaving no room for genuine choice. Both pictures feel unsatisfying. The first asks us to believe in a kind of magic. The second seems to drain life of meaning. If Orch-OR, or any similar framework, were even partly correct, it would suggest a third path, one that avoids both illusions. To see how, it helps to gently separate two ideas that are often confused: randomness and freedom. Quantum physics is often described as random. Outcomes cannot be predicted with certainty, only with probabilities. When people hear this, they sometimes leap to a hopeful conclusion. If the universe is not fully determined, then perhaps free will slips in through the gaps. But randomness alone does not give us freedom. A coin flip is unpredictable, but it is not free. A random number generator does not choose. It produces outcomes without purpose or intention. If our actions were merely the result of random quantum events, that would not give us agency. It would simply replace mechanical inevitability with noise. True freedom, whatever it is, must be something else. Here is where the idea of organized processes becomes important. In the Orch-OR picture, quantum events do not occur in isolation. They are orchestrated, shaped by neural structure, memory, goals, and context. The probabilities are not floating freely. They're constrained and influenced by the state of the entire system. Think of a musician improvising. Each note is not fully predetermined. There is openness, possibility. But the music is not random. It is guided by skill, intention, and structure. The musician shapes the space of possibilities, even though the exact sequence is not fixed in advance. Agency in this view is not about controlling outcomes with absolute precision. It is about influencing which possibilities are more likely to occur. If consciousness involves moments where physical possibilities resolve into experience, then agency may lie in how the system biases those resolutions. Not by commanding particles, but by shaping the conditions under which decisions emerge. This reframing aligns surprisingly well with lived experience. When you make a decision, it does not feel like pulling a lever that forces the universe to comply. It feels like weighing options, considering values, imagining outcomes, and then acting. The final choice often feels clear only at the moment it happens. Before that moment, there is a sense of openness. After it, a sense of commitment. This does not require supernatural intervention. It requires a system capable of integrating information, holding possibilities in tension, and resolving them in a coherent way. In this light, free will is not absolute independence from causation. It is participation in causation. You're not outside the chain of events, you are part of it. A locus where information, memory, emotion, and context converge to shape what happens next. This view also helps dissolve a common fear. Many people worry that if science explains behavior, It eliminates responsibility. If actions are caused, how can anyone be accountable? But causation does not erase agency. It defines it. We hold people responsible not because their actions are uncaused, but because they arise from who they are, from their values, understanding, and capacity to reflect. Agency depends on coherence, not on exemption from physics. Orch-OR, if true, would not undermine this. It would simply add depth to the physical story behind it. It would suggest that consciousness plays a role not by breaking laws, but by organizing how laws unfold in complex systems. The self does not stand apart from the universe. It is one of the ways the universe organizes itself. This perspective avoids despair and avoids fantasy. It does not claim that you are free in every imaginable sense. You cannot choose your genes, your early environment, or many of the forces that shape you. But within those constraints, there is room for influence, reflection, and growth. Freedom becomes a matter of degree, not an all-or-nothing property. This is perhaps why debates about free will often feel so emotionally charged. They're framed as absolutes when lived experience is not. You feel free when you act in alignment with your understanding and values. You feel constrained when those alignments are blocked. The feeling of agency tracks coherence, not metaphysical independence. Seen this way, quantum uncertainty is not the source of freedom. Organization is. Quantum processes, if involved at all, would contribute flexibility, not arbitrariness. They would provide a substrate where outcomes are not rigidly fixed, but still shaped by the system structure. This is a subtle idea, and it resists slogans. Free will is not magic. It is not randomness. It is not exemption from nature. It is the capacity of a complex system to shape its own unfolding. Whether Orch-OR is correct or not, this framing offers a calmer way to think about agency. It allows us to take science seriously without giving up on responsibility or meaning. As the story nears its end, the remaining questions widen once more. Beyond the individual, beyond the human. If consciousness depends on specific kinds of organization, what does that mean for machines? For artificial intelligence? And for the future of minds we have not yet encountered? Those questions remain open, waiting quietly at the edge of what we know. As the story reaches its final stretch, the questions widen one last time, away from individual minds and toward the boundaries of what we can imagine building, preserving, or losing. If consciousness depends on organized physical processes rather than abstract computation alone, then two of the most emotionally charged topics of our time quietly come into focus: artificial intelligence and death. They may seem unrelated, but both force us to ask the same underlying question: what does it actually take for experience to exist? Modern artificial intelligence has achieved remarkable feats. It can recognize images, generate language, diagnose disease, and play complex games at superhuman levels. From the outside, it often looks intelligent, sometimes uncannily so, and yet there is a difference that is hard to articulate. AI processes information. Humans experience information. If Orch-OR, or anything like it, were even partly correct, this distinction would matter. Classical computers operate by manipulating symbols according to rules. No matter how fast or complex the computation becomes, it remains a sequence of defined steps. The machine never occupies a genuine spread of physical possibilities. It never resolves uncertainty in the way quantum systems do. This does not make classical AI useless or inferior. It makes it different. In this view, intelligence and consciousness are not the same thing. One can exist without the other. A system can be highly capable without having inner experience. This helps explain an intuition many people already have, that even the most advanced AI feels empty in a particular way, not because it lacks complexity, but because it lacks presence. From the Orch-OR perspective, building a conscious machine would not be as simple as scaling up computation. It would require replicating the kinds of organized physical processes that give rise to conscious moments in biological systems. That does not mean adding quantum hardware alone would be enough. Quantum computers, as currently designed, are powerful tools for specific calculations, but they are not organized like brains. They are not embedded in bodies. They do not integrate memory, perception, emotion, and action into a unified pattern shaped by survival and learning. Consciousness, in this picture, is not a plug-in feature. It is an emergent property of a deeply layered system. This realization tempers both optimism and fear. It suggests that conscious AI is neither imminent nor impossible. It is simply far more complex than popular narratives imply. Turning to the other question, the tone shifts. If consciousness is a process rather than a substance, what happens when the process ends? Death has often been imagined as a transition of something that persists, a soul leaving the body, an essence continuing elsewhere. Orch-OR does not support or deny such ideas. It simply reframes the question. If consciousness depends on organized physical events, then when that organization irreversibly breaks down, conscious moments cease. This may sound bleak at first, but it also removes a particular kind of fear. There's no experience of absence. Just as anesthesia produces no felt gap, the end of consciousness would not be something one experiences. There is no darkness, no waiting, no awareness of nothingness. There is simply the final moment and then no more moments. This framing does not answer existential questions, but it clarifies them. It shifts the focus from what happens afterward to what happens now. If experience arises moment by moment, then its value does not come from permanence. It comes from presence. Each conscious moment is complete in itself. Its meaning does not depend on lasting forever. From this perspective, the fragility of consciousness is not a flaw. It is part of what makes experience precious. Patterns exist for a time. They arise, persist, and eventually dissolve. This is true of storms, melodies, ecosystems, and lives. The impermanence does not negate their reality. It defines it. Science, at its best, does not offer comfort through illusion. It offers clarity through honesty. Orch-OR may turn out to be wrong. Many bold theories do. It may be revised, absorbed into something else, or replaced entirely. That is the normal course of scientific progress. But even if it fails, the questions it raises will remain. Why does physical activity feel like anything at all? Why does experience arrive in moments? Why does organization matter more than sheer activity? These questions sit at the edge of knowledge, where physics, biology, and philosophy meet. And edges are where science has always grown. The goal is not to declare final answers, but to ask better questions, to refine our understanding of what is possible and what remains unknown. In that spirit, it is worth ending not with a conclusion, but with a pause, a recognition that consciousness, whatever its ultimate explanation, is something extraordinary, not because it is supernatural, but because it is rare, fragile, brief, and deeply personal. Whether rooted in quantum processes, classical networks, or some combination we have yet to imagine, experience remains the one thing we know from the inside. That alone makes it worth studying with care, humility, and patience. As you rest with these ideas, there is no need to hold on to them tightly. Let them drift. Let them settle. Science moves forward slowly, often revisiting old questions with new tools and gentler perspectives, and so we arrive at the edge of what we know. not with certainty, not with fear, but with quiet wonder,